Okay, welcome back to our meeting, our online meeting. Welcome to Markus's second talk on L theory of rings via higher categories.
Yeah, thank you so much. So today the first thing we want to do is finish a little bit of the discussion of some properties of this L theory space that I've indicated last time. Of course, we didn't give full proofs, but recall that we wanted to construct a space as a geometricalization of a simplicial object in spaces, which assigns to each object n the set of or the space of Poincare objects in an infinity category, a Poincare infinity category we've constructed out of the poset of non-empty faces of a delta n. So we had a little bit of discussions afterwards of how one can geometrically interpret these things. For today, I don't want to say much more about it. And then there were these two exercises at the end that say that in this L theory space, it's pi 0, the group of components, or the monoid of components is in fact a group because it's the L group, which we have already seen to be a group. And there was another exercise saying that if we do the likewise construction with the space of forms as opposed to the space of Poincare objects, this becomes contractible. So we'll utilize this exercise a little bit later today when we want to discuss the sort of the higher homotopy groups of this L theory space. Okay, so one construction that I would like to get into is the following. So I want to define a category of metabolic objects, which we, oh man, it happened again. I'm so sorry. The synchronization stopped and happened again. Are we back? No. No. Okay, finally we're back. So what I want to define is an infinity category called met C copper, and it's just the Poincare subcategory of this row 1 category on all objects which are the form of this cospan from W to X, where one of the two endpoints is 0. So recall that this category row 1 we've constructed really had objects, these cospans, W going from X to X prime, and Poincare objects in this category were precisely equivalently given as sort of Lagrangians in the sum of X comma Q and X prime comma minus Q prime. And now we just want to look at the subcategory of objects where X is 0, and we just restrict the quadratic functor. The summation structure or this Poincare structure is just restricted to the subcategory. So concretely what comes out is that the Hermitian structure or this Poincare structure that we obtain on a morphism L to X, which we view as equivalently as this datum, right? It's just one single map, is given by the fiber of copper X to copper L. So in other words, it's really a point in the space copper X, a form on X, together with a null homotopy in the restriction in L. So the Poincare objects of this metabolic category are exactly Lagrangians in the way that we defined it yesterday. Okay, so this is what we have here, this little observation that Poincare objects are precisely Lagrangians. And now I want to do a bit of more category theoretical statements. Namely, I want to consider the following sequence of stable infinity categories. So first we can look at this metabolic category C comma copper sitting here, and we can take a morphism L to X and evaluate it on the target. So we take the target map which goes to C, and I claim that this functor is canonically I don't know, a functor of Poincare infinity categories. I'll say a little bit about this in a moment. And likewise, we can look at C sitting inside the category of metabolic objects by sending Y to Y with a map to 0. So informally, we think about, I mean, if you think geometrically, then this would be a null cobordism of X, and we map it to the boundary of this null cobordism. Whereas this object would say we take a closed manifold and view it as a manifold with boundary by taking the empty boundary. So those are what these two maps are. And so the statement is that this sequence is a split Poincare-Verdier sequence. So let me tell you what this means. Jonathan will take up on this also in his lecture tomorrow. So firstly, it just means that it's both a fiber and a co-fiber sequence in the infinity category of Poincare infinity categories that we discussed a little bit yesterday in the exercises, and is such that this projection functor has both left and right adjoints if you just view it as a functor of stable infinity categories. Now, in this particular situation, it is quite easy to unwind explicitly what is meant, so or what it means to be a split Poincare Verdier sequence. And so I want to explain this rather by directly proving the essential things one has to show for this to be true, instead of giving a more formal definition now. And so the very first thing that we need to show is that this inclusion, so this is supposed to be a fully faithful functor and exactly the kernel of the target map. But clearly, I mean, the objects of the form y mapping to 0 are exactly the kernel of the target map, right? So it's clear that the image of iota is exactly the kernel of t. And then for this functor to be a Poincare functor, it is sufficient to just prove that if we restrict the quadratic structure of this quadratic functor copper along I, what we obtain is loops copper. So, I mean, this is essentially what it just means. You just restrict the quadratic functor along this inclusion. But if we just calculate what copper net of iota of y is, then we just have to look. I wrote down the formula for copper net here. So it's going to be given by copper net of y mapping to 0. That is the fiber of copper of 0 to copper of y. And copper of 0 was 0 because Q is, or copper is reduced. So this is really the loops on copper of y. And of course, this is a canonical identification. And so then the next thing we have to check in general, being a Poincare Verdier sequence. So this is essentially the statement that iota is the inclusion of the kernel of T. So it being a co-fiber sequence in general would say that the underlying functor of stable infinity categories T here is Verdier projection map. But this can be characterized very neatly if we demand the existence of left and right adjoints. It really just means that this functor T is supposed to have fully faithful left and right adjoints. Okay, but now I claim that this functor has a very canonical left adjoint. I think I wrote it down somewhere. Yes, right here. Okay, so the formula for the left adjoint is given by sending x to the diagram 0 to x. It's clearly a fully faithful functor. So we find that T is a Verdier projection. And what we have to show in addition as well is that, so that is sort of this being a Poincare Verdier sequence, or a co-fiber sequence also in cut infinity P, and not only in stable infinity categories. We have to check a compatibility of the quadratic functor copper and the quadratic functor defined on this quotient category C, copper. And in general, the formula is that this quadratic functor is left Kahn extended along this projection from the one that we have here. So this is not particularly relevant for today, because the existence of such left and right adjoints just concretely mean that split Poincare Verdier projections, so this functor being a co-fiber sequence in cut infinity P plus the existence of splits, just means that this functor T has a fully faithful left adjoint, so that we've checked, and that the functor on the quotient is given by restricting the functor on the big category along this fully faithful left adjoint. This is just general ways you can calculate left Kahn extensions. You have to, in general, restrict along the right adjoint if it exists, and because those are contrarian functors, in fact, we have to restrict along the left adjoint. So, yeah, I mean, I would suggest that you take at some point some time to digest this abstract formalism, but really the points one has to prove are just that copper net on iota calculates this quadratic functor, and we have to show that the quadratic functor on this quotient is given by just restricting the one on the metabolic category along the fully faithful left adjoint. But so this is just something you calculate explicitly, right? If you just, you know, probably have it somewhere. Yes, so Is it written somewhere? No. Okay, so let's write it down. If we calculate copper net of L of X, this is the fiber of, I suppose, copper of X to copper of 0, and then I suppose copper of X. Okay. So that is just a general construction that we find that this metabolic category relates to C copper, and it relates to C and with a shifted copper in form of such a fiber sequence or co-fiber sequence. And okay, so now there is a general theorem that we want to use, and which I will only say very few things about. So this is a theorem essentially due to Andrew Ranitsky, and in the context that we discuss it now due to Jacob Lurie. And it's the statement that the L-theory functor, the way I've defined it, as a functor from Poincare infinity categories to connected spectra, sends any Poincare-Verdier sequence to fiber sequence, in particular split ones. Put split here. Split Poincare-Verdier sequences to fiber sequences of spaces. So the general reason for such a result, or the way that Jacob, for instance, proves this, is that he observes that if you have a Poincare-Verdier projection, for instance, of this kind, well, the L-theory space was given by a geometrical realization of a simplicial space. And the theorem one proves is that if one has a Poincare-Verdier projection, then this map of simplicial spaces is a Kahn fibration of simplicial spaces. And it's a general fact that Kahn fibrations of simplicial spaces geometrically realize to to fiber sequences. So it's some map of simplicial spaces is a Kahn fibration. It has some lifting property. For this, you just make explicit what these row constructions do. You prove that lifting property, and then you deduce that after applying realizations, you obtain a fiber sequence. So L-theory will send such Poincare-Verdier sequences to fiber sequence. And so we want to use this to prove something about the homotopy groups of the L-theory space. And the way we do this is as follows. It's the proposition that says that the nth homotopy group of the L-theory space C copper is isomorphic to the 0th L group in the way we've defined it in the last lecture of C with the n-fold looped copper, which is again a quadratic functor and reduced to excisor. Okay, so how do we prove such a proposition? So of course we induct over n, because n equals to 0 was exercise 9. That was the statement that the 0th homotopy group of this L-theory space is just the L group that we have. And now if n is greater or equals to 1, then we look at this Poincare-Verdier sequence, which was given by C loops copper, the metabolic category, and C copper, and apply the long exact sequence in homotopy groups associated to this L-theory fiber sequence. So what we obtain is a sequence which has pi n of the L-theory space of the metabolic category, mapping to pi n of the L-theory space of C copper, which in turn maps to pi n minus 1 of the L-theory space of loops copper. And by induction, we know that this is the L0 of C loops n minus 1 of loops copper, which of course is loops n copper. And then the next term is again pi n minus 1 of L of the metabolic category. So in particular, what we see is that it suffices to prove that this L-theory space of the metabolic category is contractible. Okay, so this is what we want to show. And there's there are different ways one can do this, and one way one can is as follows. Let me put this here. So we just have to understand or recall again what the L-theory of this metabolic category is. So we will unravel definitions a little bit. So it was given by applying the taking the geometric realization of sending n to the row n category associated to this metabolic category C copper. And now the observation that we want to use is that we can sort of commute the row n construction with this metabolic construction. So I told you that for any Poincare infinity category C copper, you can apply met to it. It produces a new one. So in particular, I can do it for row n and vice versa. Now, I claim that those categories are just equivalent, and on underlying categories, let's observe what this was. So on this side, the row n category of the metabolic category was given by functors from the phase poset of delta n, or its opposite, to the underlying category of the metabolic category, which is functors from delta 1 to c. And on this side, it was functors from delta 1 to, well, functors from the phase poset. So they're clearly equivalent, that's fine. And on quadratic functors, you make, or on these Poincare structures, you make use of the fact that the metabolic category sort of takes a fiber of a map of objects, and the row n category takes a limit of a big diagram. And in the other direction, we first take fibers and then take a limit, or I mean, or the other way around. Right? Imagine that for the row n of med C copper, you have an arrow of n adds, and then you can either take first limits or fibers, or first fibers and limits. Okay, so yeah, this is just an explicit check that these two categories are just canonically equivalent. So what we now wish to use is the following proposition of Ranitzky, which is for some reason that I actually don't quite understand, and maybe we can find out in the discussion session later. It's called an algebraic tome isomorphism, and the statement is that the space of Poincare objects of the metabolic category canonically identifies with the space of all forms in C, but with a shifted quadratic functor omega copper. Okay, and again, there are many ways one can prove, I mean, at least two ways one can prove this result, and I want to convince you of the following argument that one can employ here. It's, oops, okay, so let's do it like this. Okay, so let me not say I give a proof, but rather a reason why this should be true. So I want to say that this infinity category of Poincare infinity categories, where, right, remember, objects are the Poincare infinity categories and morphisms are non-degenerate functors. So functors which come equipped with a canonical transformation between the two Poincare structures we have, subject to a non-degeneracy condition. And there's also a category of what we call Hermitian infinity categories, where in both the objects, we forget about the non-degeneracy condition, and also in the morphisms. So in other words, the objects of this category are really just C and copper, where this is reduced to excisive, and no further condition is required, and morphisms are functors from C to C prime, together with a natural transformation from, I suppose, copper to copper prime composed with F op, again, without any further non-degeneracy condition. So there's a forgetful functor which forgets that these Poincare infinity categories have all these non-degeneracy conditions, and it's a fact that this forgetful functor has both a left adjoint and a right adjoint, and in addition, the right adjoint has the following property that if you evaluate it on a Poincare infinity category, or the underlying Hermitian category of a Poincare infinity category, what you get out is the metabolic category of C with the suspended quadratic functor. So that is a fact. I don't want to explain more about this, but from here, I've indicated last time that the space of Poincare objects is in fact, I mean, taking the Poincare objects in some infinity category is a functor which is co-represented by a particular Poincare infinity category that also appeared in Jonathan's talk. It's just a finite spectra with a particular, what we call the universal quadratic functor. Again, it's not terribly important to know exactly what this object is for now. I just want to say that the space of Poincare objects will be the mapping space in cut infinity P from these finite spectra with the universal functor, and well, then we have to map to the metabolic category in C copper. And now by this adjunction property, here we find that it's the same thing as, all right, first we use that, we now write the metabolic category as the right adjoint applied to the underlying category of C and groups copper. And now by adjunction, this is the same as the mapping space in Hermitian categories. And maybe it's not very surprising that in Hermitian categories, this very object will represent the space of all forms. So this category of finite spectra with the universal quadratic functor, in the world of Poincare categories, it co-represents the Poincare space functor, and in the world of Hermitian categories, it co-represents the space of all forms. And so one way of seeing this algebraic tone isomorphism is just the statement that the metabolic category is when it takes the value of a right adjoint, and then it's just an adjunction argument. Okay, let me also say that that we will be able to make this equivalence, which is now very abstract, a bit more concrete in a couple of moments. So this is an instance of algebraic surgery, and I will explain the general procedure of algebraic surgery in a couple of minutes. Nevertheless, what we then find is that the L-theory space of the metabolic category is the geometricalization of the space of Poincare objects on row n of the metabolic category. Now, with our observation at the very top of the page here, we're allowed to commute the metabolic category and the row n construction in this step, and obtain the simplicial space which sends n to the Poincare objects of some metabolic category, which is now the same thing as the space of forms of row n. And now it's exercise, not 1, but 11. Exercise, well, maybe it was 10, I don't know. The last exercise we had says that, well, realizing the space of forms of row n is a point. So nothing happens. So this is one way you can sort of prove that the higher L groups are in fact just the L groups of some shifted quadratic functor. And essentially this is really the way Andrew had already also proved that that sort of the L spectrum that he constructed was an omega spectrum, i.e. that one can give a presentation of its homotopy groups. We know that all homotopy groups of this L spectrum have generators and relations description which are sort of uniform in N, right? It's always just given by Poincare objects in some particular infinity category, subject to the relation that things are 0 if they admit a Lagrangian. And this is also something that appeared in Jonathan's lectures, where he defined the L groups as some homotopy group of the geometricalization of the cobordism category. So if you look at his lectures again, you will find that these things precisely match up. That I suppose that this term is essentially what Jonathan defined L groups to be, the nth L group of C to be, and well, we've now seen that in fact those are the homotopy groups of the canonical L theory space you can construct, making use of this row n add construction. Okay, so I wanted to indicate that we can control the higher L groups even if we've constructed a priori a space, an L theory space, and just use some general properties that this construction has, i.e. that it sends certain split Poincare Verdier sequences to fiber sequences, and that we can calculate that the L theory of the metabolic category vanishes. Okay, so what we want to do today, the next thing we want to do is essentially keep in mind always the question, what is the relation between the symmetric Witt group of the ring that we've constructed and things like, say, the 0th L group of the derived category with maybe the genuine symmetric structure that we wrote down, or maybe also the symmetric structure. I mean, I don't know, we had different variants of symmetric forms in this general context. And we want to understand what is the relation between these naive Witt groups built on projective modules and the L groups constructed in this more general context. And the main difference that you should immediately see and remember is that objects in here are really all represented by finitely generated projective modules equipped with a form. Whereas objects here are represented by some chain complex equipped with some homotopical version of a form, right? Some notion of an abstract form. But these chain complexes might be huge, and one way of relating these two is to understand to what extent can we represent elements in this L group by complexes which are in fact very short, which are just given by a finitely generated projective sitting in a single degree. And the process of making a general complex representing an element in the L group smaller and smaller is the notion of algebraic surgery. And that is the construction that I want to explain next. And then we'll utilize this in various ways. Okay, so a definition is that a surgery datum on a form x comma q, and by a form I mean just a Hermitian object, a form object for some stable infinity category C equipped with a Poincare structure. So it consists of the pair S and eta, where S in fact comes with a map to X, F, and eta is a null homotopy of Q, of the restriction of the form Q to S. So it's very much the same as what is a Lagrangian, but we don't demand that any condition holds, right? We just say we want to have a null homotopy without any further condition of what this might or might not induce. So S might be a Lagrangian, but it might also not be a Lagrangian inside X. And precisely what this is, these surgery data are just points of the space of forms on the metabolic category, which lie over that particular form object xq along this functor T that we've constructed in the last lecture, in the beginning of the lecture. Right? So this is just what a surgery datum is. And associated to a surgery datum, we want to perform a surgery, or so we want to change our object xq to a different but cobordant object, so representing the same class in the L theory group. And the statement in this direction is the following proposition. So the statement is that there is a Poincare functor, let's call it chi, from the metabolic category of CQ to the one category of C proper, which sends a surgery datum to something that we call the trace of its surgery. I'll come to this in a moment. And this functor in two spaces. And so what are these spaces? So here we take a form, here we take a form for the metabolic category, and then we can look at its boundary. So the point it lies over, so this we can extract this point xq out of the form on the metabolic category, and we demand that this form is in fact a Poincare form. So in other words, this space is really just a Poincare object together with a surgery datum on it. Might be a Lagrangian, might not be a Lagrangian. And on the other hand side, we can look at the space of Poincare objects in row 1 CQ, which last time we've seen is essentially given by cobordisms between two Poincare objects. And I want to make this a bit more concrete, but that's good. So instead of really proving this proposition, I want to tell you what is the association on objects, roughly how do we get the form on this output. I mean, how can we actually construct a Poincare object in this row category if we start out with a point in this space, and indicate roughly why there might be an equivalence of the sort that I explained. So, but proving this proposition is beyond the scope of the lectures. I don't want to get into this. But we can do the following construction. So associated to a surgery datum S with a map to X and this null homotopy eta of the restriction of Q on X, you can do the following diagram. So you look at F mapping from S to X, and you can first construct this vertical cofiber sequence, S to X modulo S, and then you can again take, so let me say that this first vertical map is constructed by mapping first X, you identify again with the dual, the proper dual of X, and then you dualize F and map to the proper dual of X. Okay, so this is the map which is the left horizontal one, so this map. And the fact that eta provides a null homotopy of the restriction of Q exactly means, again, that this diagram is filled, right? And remember, the surgery datum SF and eta was called a Lagrangian if and only if this diagram is a pullback. That was the definition of a Lagrangian. We already had this diagram there, and then said it's a Lagrangian if and only if it's a pullback. Now we don't care if it's a pullback or not. So what we do is we just extend this diagram. Well, I mean, because there's a 0 up here, we can also take this vertical co-fiber sequence on the right, obtain a commutative diagram here, and then what we do is we take vertical or horizontal fibers. So we define these terms as to be fiber sequences, and again obtain a diagram of this sort, where now this left lower term is a pullback diagram. And the span we wish to associate to the surgery datum, right? We have to construct an object in this P1 category, in this row 1 category, which consists exactly of cospans, and the cospan we look at is exactly the one that's highlighted here. So one term, one side, one boundary component is X, and the other one is something new. And chi F, so this term in the middle, this is usually referred to as the trace of the surgery. Or maybe the whole cospan is referred to as the trace of the surgery. So this is certainly a construction on the level of underlying objects that you can do. Now let me indicate very briefly how one can construct a Poincare, or I mean at least the form on this cospan. So what we have to produce very concretely is a form on XS restricting to well, and a homotopy between the restriction of the form that we've constructed on XS to the restriction of the form of Q along alpha. This is the concrete datum that we have to produce. And the way we do this is as follows. So we look at this horizontal, sorry, at this vertical co-fiber sequence. And associated to it, we can look at the copper and copper of chi of f. So this is the restriction along this map that I call beta here. Sorry, along this map that is S to chi of f. And now you can do the following construction by definition of the duality associated to copper. There is a canonical map. There is this canonical map. So this right vertical map is a canonical map. And let me indicate also, maybe I need a different color for this. So this map here is the composition of chi of copper of chi of f, mapping to maps of, I suppose, chi of f to dual of chi of f, and then we can restrict along the given map that we have. Right? Because there's a map from S to chi of f, then we can take the dual of this map and post-compose with this. So that's what this left vertical map is. And now it's a proposition, a general fact, that this term chi of the copper of XS, so the space of forms in which we wish to produce a point, so this space, this is the total homotopy fiber of this commutative diagram. i.e., what we have to do is we have to take the, say, horizontal fibers, like here and here. Then there is an induced map between these horizontal fibers, and then this sequence is also a fiber sequence. So that's a general thing you have to believe me. And then I invite you to have a look at this concrete diagram that I wrote down and convince yourself that you can, starting with this form, starting with the form alpha upper star of Q, right? We have Q, a form here, so we can restrict it to a point in copper of chi f. And with this object we can start. We easily see that it is sent to 0 under copper of S. So it lifts to some point over here. And then you just have to check that this point is canonically sent to 0 again, and so it hence lifts once more. So this is sort of tracing definitions. It is a bit complicated, but I invite you to sit down at some point with some quiet time and think. But this is somehow one way one constructs this form on the output of the surgery. It's not a very easy construction, but okay, that's what it is. So I mean, essentially wanted to indicate how this how the form is roughly constructed. So what we end up with is essentially I've indicated what this functor chi does on forms. Right? If you take a form that was exactly a Lagrangian, or I mean the surgery datum, from it we want to produce a new form in this row 1 category, which was exactly a span and a form on XS, such that the two restrictions are identified. And so what I want to indicate very briefly is the fact that this particular construction restricts at least to an equivalence if we restrict further along not only forms in this metabolic category, which lie over a Poincare object, so the surgery datum on any object, but we can look at surgery data on 0 instead. And so what is supposed to come out is exactly this equivalence, which is precisely the content of the algebraic tome isomorphism. Okay, so I've written down a couple of constructions, how one passes back and forth from this. So the message I want you to take from this is essentially the statement that this very general algebraic tome isomorphism that I've alluded to earlier, which was argued by an adjunction, is in fact just in a particular instance of performing surgeries on the 0 object, essentially. Taking a 0 object, taking a surgery datum on that, and performing the surgery, that exactly implements this algebraic tome isomorphism. But because it's not particularly important for the rest of this lectures, I want to leave it at that, but invite you to have a look later also, or if you're watching on YouTube, just pause and breathe through this construction a little bit. In any case, I more or less wanted to convince you that although many of these things are very abstract, it's still a very concrete. You have to construct particular elements, show that certain lifts exist, and then you just go through with this. Okay, so we want to use this general construction of algebraic surgery to prove something about the map from a map from the symmetric Witt group of a ring to the 0th L group of the derived category of R with coefficients in, with Poincare structure given by this genuine symmetric one. And we want to show that this map is an isomorphism. And in particular, what we need to do is we need to argue that up to cobordism, Poincare objects for this Poincare structure can be assumed to be of the form exactly a projective module sitting in degree 0, viewed as a finitely as a perfect chain complex. And okay, so this is the kind of arguments that we want to do now in the following. Oops. Okay. So first we need a following lemma, which says that if you take a ring and an invertible module with involution, as always, then the following two statements are equivalent. Namely, firstly, X is an M connective, and its dual is minus N connective. So let me remind you that X is M connective. That just means that, well, if we think about it as chain complexes, then the ith homology group of X is 0 if I is less than M. And sometimes I will also write pi I of X because I think of chain complexes also as spectra, but this is just really equal notation. If you're confused, whenever I write pi I probably mean HI, just the homology of this chain complex. So the statement is that if X is M connective, so has no homology below degree M, and its dual is minus N connective, so has no homology below dimension minus N, then X is represented by a chain complex, which looks as follows. It has finitely generated projective modules, Pi, sitting in degree I, starting with Pn, having nothing to the left, and ending at Pn and having nothing to the right. Okay? So I've added a little proof of this, I think. Oops. Okay, sorry. So let me just go through this very quickly. So the first step is that you say, well, because X is a perfect complex, it's represented by some finite chain complex C, whose groups Ci are finitely generated projective, and finite means that almost all of them are 0. Then step 2 is that you say, because X is M connective, you can achieve that the groups below degree n are 0 by just a concrete replacement of your chain complex. And then you use that everything was projective, and you can just cut off the terms that are below degree m. Then you use that the dual of X is represented by, well, take your particular chain complex you had and just apply hom r blank m to it everywhere, because the chain complex consisted of finitely generated projectives. So this is just a way of representing the dual of X. And now, because the dual of X is minus n connective and C had no terms in degrees less or equal or less than n, if you've applied hom to it, then things will turn around. You make the same argument for the dual of X, will achieve that these new groups can be assumed 0 for I less than minus n. And then you dualize again and achieve that X, which is isomorphic to the double dual, is now of the claimed shape. This is that you do, right? So it's really, you just represent, cut off, dualize, cut off, and dualize again, and then you're done. Okay, but this is very good because it allows us to say or to phrase that a chain complex is concentrated in a, or is represented by chain complexes concentrated in a certain range of degrees in terms of connectivity estimates on both X and its dual. And that's a very convenient tool to just say that, well, I need to show that the complex is sort of so-and-so connective, and then maybe some other dual is so-and-so connective. Okay, so let's make a definition and have R and M as always, copper B and N compatible Poincare structure, and assume for now that copper of P is an Algebraic spectrum in degree 0 whenever P is a finitely generated projective module. For instance, copper GS or copper GQ, which was equivalently given by these, copper greater or equals to N, or I don't know, copper of this Burnside ring or whatever. I mean, there are many such examples that we saw, but the genuine symmetric one that we've discussed yesterday is one of them. So that's the one to keep in mind. Here. Okay, in this context, I want to define a Witt group of these projective modules with sort of coefficients in copper as just being isomorphism classes of copper forms on finitely generated projective modules. So that means a copper form is just a finitely generated projective equipped with a point in copper of that finitely generated projective. That's just an Abelian group by assumption. Pick a point in that Abelian group. And again, you divide out the submonoid spanned by all metabolic forms. So these are sometimes also called strictly metabolic. So I really want to, I want this actual projective module to have a projective submodule on which copper vanishes such that some exact sequence or some sequence is exact, just as we had last time. And the proposition we want to prove is that under these assumptions that we had, so Rm, as always, copper M compatible and copper sends projective modules to Einberg-MacLane spectra concentrated in degree 0, then there's a canonical map from the Witt group of projective modules to the 0th L group of the derived category with coefficients in copper, and this map is an isomorphism. Okay, so again, what is this map? I mean, by what is this map induced? Well, it is take a projective module with a form, view it as a chain complex with that particular same form, and that defines a map before quotienting out metabolic forms, and then if something was sort of strictly metabolic, it's in particular metabolic in this more general sense where we allowed any sort of Lagrangian to happen. And I just saw that here I should also use modular forms, of course. Okay, so again, the main difference is on the left-hand side, things are projective modules. On the right-hand side, things are chain complexes, or represented by chain complexes. And okay, so let's try to see why this map might be an isomorphism. Oops. Okay, so let me argue about surjectivity first. So suppose you have any Poincare object for copper representing an element in this L group. So if X is connective, what happens? Well, then X, it's already isomorphic to its dual, right? Because it's a Poincare object, and hence the dual is also connective. And recall that connective means zero connective. So by the above lemma that we've had here, we can represent it by a complex which is concentrated in degree 0 and is finitely generated projective there. So in other words, the finitely generated projective modules sitting in degree 0 are precisely those perfect complexes which are both connective and whose dual is also connective. Okay, so in this case, we're done. That's good. And in general, assume that X is minus K connective for some non-negative K. Because else, you can convince yourself that the self-duality will imply that X is in fact 0. And assume that minus K is the minimal of all I such that pi I is non-zero. So in other words, I want pi minus K to be the smallest non-zero homotopy group of this perfect complex X. Right? There is going to be a smallest one, and then take that one. So by the lemma, or any other argument you wish, there will be a projective module, which finitely generated projective, which comes with a surjection to pi minus K. For instance, represent your complex by one which ends at that minus Kth term, and just pick that very last projective module. And clearly it will have a surjection onto the homology at that point. Okay, and from this we obtain a map of chain complexes from P sitting in degree minus K to X, a map in the derived category. And now the statement is that this we wish to show as a surgery datum. So in other words, we need to show that the form on X restricted along this map F will vanish in the space of forms on P shifted in degree minus K. But the assumption is made in a way that this space is K connective. And because K was assumed to be greater, space is connected, and hence any form is null homotopy. Right? So just pick any null homotopy like this, and we obtain a surgery datum of that kind. And now it's a good exercise to familiarize yourself with the definition of the surgery output is that, well, if you perform surgery, then you will get a new Poincare object. And the only thing that we want to know about this object is that this is a bit better connective than the one that we had before. So in particular, the exercise is to show that it's minus K plus 1 connective. Okay? And once we have this, then, I mean, we induct. It's again a perfect complex. The lowest homotopy group admits a surjection from some finitely generated projective. You do the same argument and induct, and at the end of the day, we're done. So this shows surjectivity of this map. Because the assumption on this quadratic functor were really made as to ensure that we can just kill all homology that this chain complex might have by successive surgeries. This was just the assumption on the Poincare structure. And now injectivity is a similar argument. What one does, I mean, I just want to phrase this very briefly, but I invite you to look in the notes and also work up these exercises that I should make in a better color, I suppose. So the essential idea is that for Lagrangians, you want to make a similar argument. Oops. Make this color like this. So for Lagrangians, we make the following point. Actually, a bit subtle. So let me say something about it. So suppose we're now giving a finitely generated projective with a form in proper of R, and assume that its image in the L group of chain complexes is 0. In other words, what we find is a map of chain complexes from some perfect complex L to P0 and a null homotopy of the restriction. And okay, this is supposed to be a Lagrangian. So in addition, we know that this sequence is a fiber sequence. And I've tried to explain earlier that these Lagrangians are exactly Poincare objects in the metabolic category, right? And so we can now view just this object as a Poincare object somewhere and try to perform surgery in this bigger category of metabolic objects. So, I mean, the general construction had nothing to do with chain complexes, right? It was just some stable infinity category and the surgery datum, then you can perform surgery. And the way we now want to do this is use such surgeries in the metabolic category to make this Lagrangian L at least -1 connected. And then there's the exercise that tells you that suppose you found a -1 connective Lagrangian of your fixed object P0 equipped with this form Q, then the exercise is to show that in fact L is represented by a chain complex with just two groups, Q and N, sitting in degree 0 and -1. Okay, so that's a little exercise to show that once L is -1 connective, we can arrange that L is represented by such a complex. And the proof that L can be made -1 connective is sort of verbatim the same thing as before, right? You just imagine it's not, look at the lowest homotopy group, find the surjection, and then you make a little, the argument a little bit different than before. In fact, what you do is you take this map Q in degree -k to L and look at such a diagram. So what you have to ensure is that the composite from Q minus K to L and then further to P, which was part of this, you know, the Lagrangian structure F, that this composite is null homotopic, right? I mean, because else you cannot fill this diagram. But this is the fact because Q and P are both projective, so the space of maps from Q to P, once, you know, minus K is sufficiently small, is going to be 0. There are no such maps. So just for formal reasons, this map is null homotopic. And you can view this square as a morphism in the metabolic category and just calculate that it's a surgery datum. Then you perform surgery, and it's another exercise then to see that the surgery output is of the form unchanged. And we change the Lagrangian to something which is now -k plus 1. Okay, so it's essentially the same argument as in the case for surjective things, and is very much along the lines that we all know, right? That injectivity is just a relative form of surjectivity. You just have to lift the relation. And now what we do is we just perform these surgeries on the witness of our form being 0, so on the Lagrangian itself. There are many ways to implement this. This is one that you can do. So what we obtain at the end of the day is the following. Inductively, we find that we can assume that we've now found a Lagrangian which is -1 connective. And it's also good to convince yourself that you cannot make it better, right? Once it's -1 connective, you can try to perform surgery, but then you can convince yourself that, that it will not become better connective. In any case, we can assume that L is -1 connected with this procedure. And then in this exercise 12, we've convinced ourselves that we can then write L as this chain complex, just having Q and N sitting in degree 0 and -1, and hence find the map from N sitting in degree -1 to L, right? So this is, what is this map? Just this map of that chain complex, 0 and N. Mapping to Q to N, right? That's a perfectly valid map of chain complexes. And its cofiber is, of course, Q sitting in degree 0. And now you do this fun trick to show that we now consider this diagram as a morphism in the metabolic category, from the identity to this Lagrangian L to P. And again, you calculate that the restriction of the form is 0 for trivial reasons. Just the space of all forms on this object is 0. So again, this is a surgery datum, so we can do surgery. And then, okay, I invite you to look at these notes in more detail if you wish. But the point is that what comes out is that the output of surgery constructs a Lagrangian sitting inside the following object. It's P, and then you add on it n plus the dual of n. But now note, all of these modules are just finitely generated projective modules sitting in degree 0. So all of them represent points in this Witt group of projective modules that I've constructed. And in fact, this sum represents 0 because it comes with a Lagrangian which also sits in degree 0. That is the essential point. And furthermore, this particular Poincare object n plus dual n comes with a Lagrangian which is dual n. So I think I wrote this somewhere. Yes. So here we observe that n plus dual n comes with a Lagrangian, which is the inclusion of dual n to n plus dual n. And so that means that in this Witt group, we can write PQ as the same as PQ plus n plus dual n, because this is 0, as it has a Lagrangian. But the sum of these two forms is then just given by P plus n plus dual n. But that again has a Lagrangian named Q. So this is 0, and hence PQ is 0. Okay, so this is a slightly complicated argument, but I invite you to really sit down and try to understand the logic of this argument. For surjectivity, let's recall, we really only say we have to make a complex highly connected, and we just perform surgeries from below, and there's no obstruction to doing so. Now, to prove injectivity, first we say, well, we have any Lagrangian on an object over an object which is already very connective. Then we first make the Lagrangian as connective as we can for formal reasons. What remains is a complex which is concentrated in degrees -1 and 0. And on that, we make this weird other kind of surgery that we've constructed using this kind of surgery data. Yeah. So that is essentially the argument why the L group associated to such a Poincare structure, which sends projective modules to things sitting exactly in degree 0, is a purely algebraic thing. It is really just a Witt group of projective modules with actual forms modeled out by actual metabolic objects. Okay, so that is the upshot to take away from here. Good, so let me continue with another point right here. With this corollary that the 0th L group of the derived category with respect to this genuine symmetric structure or this genuine quadratic structure, both of these have this property that they send projectives to things in degree 0. So they're really given by the symmetric Witt group and the quadratic Witt group that I've defined in the first lecture. Okay, so that is the key corollary, that these surgeries allowed us to prove that the general L theory associated to such chain complexes equipped with these general forms associated to these Poincare structures, copper GS and copper GQ, in fact are purely algebraic. Okay, so I will take a couple of more minutes to go through a slight generalization of this situation. So let me make a definition for this. Essentially, we want to gather what are the properties that we've really used. And so what we want to consider are Poincare structures copper, which are M compatible and associated to a map, say n, mapping to n to the Tate C2 of R modules, as we've described yesterday, right? We said every compatible Poincare structure is determined by an R module n together with a map to n to the Tate C2. And now we say that copper is n quadratic if n is m connective, okay? So again, that just means that its homotopy groups is 0 below degree n. And we say that copper is R symmetric if the fiber is minus R truncated, which means that the homotopy groups of the fiber of alpha, so the fiber of this map, is 0 for I greater than minus R. It has only homotopy groups in the low range. So the M quadraticity is something that will appear in an argument very similar to the one that we've seen. R-symmetric structures are things that we will encounter soon. Okay, so little exercise about this is to show that a Poincare structure, which is compatible with the module M that we had, is M quadratic if and only if the linear approximation of copper associated to X is M plus K connective whenever the dual of X is K connective. Okay, that's, that's something that we're going to use at some point. And it's just a, I don't know, it's a good maneuvering of how do I calculate the linear approximation in terms of n and all these things, and how do I use that n gives us a duality and all these things to see that being m quadratic really tells us that the linear approximation has a certain connectivity property once I evaluate on objects which themselves have a certain connectivity property. And likewise, copper is R-symmetric if and only if this fiber of the map from copper X to copper S of X, so that in this nice diagram we always had was the left vertical map is minus R minus K truncated whenever X is K connected. Okay, so those are just one little things one can do. And now I see that I've forgotten to make things small, so let me just in the remaining minutes go through some of the points that we have here. So the essential goal of the remaining 3.5 minutes of my talk today and the lecture on Thursday will be to make qualitative statements about the comparison map fixing a Poincare structure copper. Then we want to make qualitative statements about the comparison map from the quadratic Poincare structure and to the map to the symmetric Poincare structure. So this does not come by chance. At the end of the day, the final lecture I want to explain, or in the final lecture I want to explain how to calculate these genuine symmetric L groups for certain Dedekind rings, and in a large range they will be determined by exactly symmetric and quadratic counterparts, and this is the main input that we have to use for this. So it's really about understanding the difference between the L groups once we vary between the quadratic and the symmetric structure. And recall that we have already calculated L0 of such a Poincare structure in terms of classical forms once we know that copper of P is an Albert-MacLane spectrum in degree 0. But we want to maybe make some more general arguments. And okay, so the theorem that we will prove is that if we have an emphatic Poincare structure copper, then the comparison map from the quadratic L groups to the L groups of this particular Poincare structure is an isomorphism in a range depending only on n. So okay, the precise numbers are n is less or equal to n minus 3, and it's surjective in degrees n less or equals to n minus 2. But essentially the statement is that fixing an m and an m quadratic Poincare structure, then in low degrees, below roughly 2 times m, the comparison map from quadratic L theory is an isomorphism. So in particular, we can calculate the L groups of this one in a low degree in terms of the L groups of that one. And okay, so maybe I will go slightly over time. I'm sorry. So I want to at least tell you the sketch of or some parts of the proof idea. So we have a couple of steps. So the first step is as follows. So what we want to show is that elements in both sides of the points that we want to compare can be represented by complexes x, q, such that x is minus k connective, say if n is 2k or 2k minus 1. Right? So we write n as something like 2k or 2k minus 1, depending on the parity, and then we want to claim that elements both here and here can be represented by complexes which are minus k connective. Okay, so I will go through the argument next time, but that's roughly what we want to say. Then step 2 will be that for minus k connective such complexes x, the canonical map of sort of honestly quadratic forms to the particular forms given by our copper is pi naught surjective. So in other words, we can in fact lift any form with respect to copper to a form with respect to this copper Q, provided our complexes have a certain connectivity bound. And then step 3 says that, well, we make a similar argument for Lagrangian And altogether, this will at least prove surjectivity of the map in question. And then again, one does a relative case to prove injectivity. But you see that one of the key steps is to prove that both sides have the property that complexes can be represented by complexes which have a certain connectivity bound. And for such complexes, just the sort of the set of forms, pi zero of the space of forms agrees, and so we can start lifting things around. In general, the space of forms will not agree, but since we can get this connectivity estimates done by surgeries, then we can start comparing. And we'll do an elaboration of such kinds of arguments next time. And for today, I apologize for going over time. I invite you to go to the forum, solve exercises, ask questions, and finish for today. Thanks.
All right, thank you.
I mean, sorry about the last thing. Is it enough that pi zero of the space of forms agree, or do we also need pi one?
I think, well, so I wrote down is pi zero surjective, so I suppose that is correct. I mean, I could imagine that what I have here is a proof idea for surjectivity.
Yes.
And I suppose that you're probably right. And yeah, I think it's yes, I think the proof actually shows that it's pi zero bijective. And maybe even that pi one is surjective still.
Yeah, I'm always confused because somehow, in order to say that it's Poincaré, you need to say that a certain sequence is exact. But in the case you're projective in degree zero, it doesn't depend on the homotopy. But in full generality, probably does. Maybe not. I'm always.
No. I think you're mistaking something. So the question whether or not a particular Poincaré object is a particular form object is Poincaré only depends on the image in copper S of X. So once I can lift, I mean, it's immediately also Poincaré lift.
Yes, but I mean, then you have a Lagrangian, and then, okay, maybe I should have said whatever. I mean, you know what I mean. Yeah,
yes.
Sorry. I mean, the way I phrased it is, yeah.
Yes. No. So on objects, there is no issue. And for Lagrangians, I agree that one has to do something. And I mean, yeah, we can all be curious if I had an argument for that or not next time.
All right, do we have further quick questions at the end of the session? No? Okay, then let's thank our speaker again.